Hello, welcome to another module in this massive open online course. So, we have looked at the classification of signals and we have looked at various classes of signals or various frequently occurring signals. Let us now start discussing the other aspect or the other fundamental aspect of this course, which is systems, their behavior and their properties. So, what we want to start looking at is basically something equally if not more important, which is the classification of systems. Okay. And when I say a system or its representation, for us the system and its representation are going to be equivalent, because frequently we are going to be dealing with a mathematical or an analytical representation of a system. So, a system representation, which we will frequently refer to simply as a system, or basically a representation or a system model, correct, is a mathematical system or a system representation is a mathematical model, correct, for an actual physical process or a physical device or an object. It is an analytical model or a mathematical model that precisely captures the input output relationship of the system. That is, given an input signal, what is the behavior of the system or what is the output that is given out by the system. So, it is a mathematical representation of a physical process which characterizes this input output system. That for us is going to be a system or a representation of the system. Okay. So, a representation of a system, that is basically it is precise mathematical model for a physical process or device, that describes the output signal for any given input signal. So, for any given input signal, the system model or system representation must be able to characterize the output, precisely characterize the output for the given input. That for us is a system. Okay. And the system is typically presented as mathematically as xt, a general system, or as one of the most frequent representations used is yt equals t of xt. Okay. This is one of the most frequently used representation, where t is basically captures this physical process or the system, x is the input signal, and y, this is the output signal. And it is also schematically represented, and this is a system, or basically it can also think it as or think of it as a transformation. Okay. For us it is also going to be a transformation. Or it is also going to be an input output mapping. Okay. So, this is your system, there is an input signal x of t, there is an output signal y of t, and this is our system. This is our system, or this is our definition first, and more precisely this is a continuous time system. In the same manner, I can define also a discrete time system where the output is y of n and the input is x of n. Okay. So, I can similarly have y of n equals t of x of n, and the properties are similar. So, this is basically a discrete time version of this, and similarly I can have a representation that is x of n is the input and y of n is the output. Okay. X of t also frequently simply referred as the input, y of t simply referred to as the output. Okay. This is the input output, characterizes system, precisely characterizes the input output relation, gives a mathematical model for the input output relation, that is, given an input signal, what is the output signal. Okay. Now, there are several systems. Again, let us now start looking at a classification similar to classification of signals to better understand the properties, classification of so let us start with a classification of system to better understand the properties of various system. Okay. The first important class of systems that we are going to look at is systems with memory and memory-less systems. That is, systems can either have memory or they can be that is, these are two different kinds of systems, memory less. Memory less systems. Okay. Now, the system is memory less, that is, it is known as a memory less system implies if output depends only on, that is both for discrete and continuous time, output depends only on current input, that is input at current time, or in current only on current input or input at current time instant. Input at the current time. That is, the past inputs or the past history of the signal has no bearing on the output of the system, and this is an important property. Alright. So, this characterizes a memory less system. For instance, you have y of t equals some constant k times x of t. For instance, in a circuit we have v of t equals r, from the Ohm's law we have v of t equals r times I of t, v is the voltage I is the current, R is the resistance, R is the resistance, okay, and the current voltage, the voltage at time instant t depends only on the current at time instant t. All right. So, this is a classic example of a memory less system. All right. Similarly, I can have for a discrete time signal, I can have y of n equals some constant k times x of n. Again, this is an example of a memory less. All these are basically your memory less. All these are basically examples of memory less systems. On the other hand, in systems with memory, they are opposite of naturally systems which have memory or systems with memory. These are the opposite of memory. These are the opposite of memory less systems, and in which the output depends not only on the current input at the current time instant, but also input at the past time instants, or the inputs at the past time instants. Okay. So, the output depends not only on x t, but also depends on the past values of x t. So, the output, let us call this output y t naught, output y t naught t naught depends not only on x t naught, but also x t for t less than t naught. That is the key, correct, x t for t less than t naught. That is, output depends also, output y t naught depends also on past values of output y t naught depends also on the past values of the signal x t, and this is known as a system with memory. For instance, again one can look at some quick examples. For instance, if you again go back to the example of circuits, you can have the voltage V t equals 1 over c integral minus infinity to infinity I of tau d tau, where V of t is a voltage. This is a voltage signal, this is the current signal, and this is the value of the capacitance, correct. This is the value of the capacitance, and what this says is the voltage current relation. This, the capacitor is a system with a memory, and I am sure this you also know from your analysis knowledge of some basic circuits, that the capacitor has memory because the current voltage depends not only on the value of the current at this time instant t, but also on the values of the current signal I t at the past time instant. So, this is the classic example of a system with memory. Unlike a resistance which is governed by Ohm's law and does not have memory, a capacitor is a system with memory. So, this is a system with memory. So, capacitor is a system with memory. Capacitor is a system with memory. Okay. So, which means current values of voltage depend on past values of the current signal. If you treat this as an input output system where the input is current, output equal to voltage, okay, current value, the present values of the voltage depend also on the past values of the current signal. Okay. So, the capacitor is a system, classic example of a system with memory. Okay. Let us now come to yet another important property of a system, that is causality, that is causal versus non-causal systems. Causal and non-causal and non-causal systems. Okay. Now, causal system, causal implies, or a system is causal if output depends only on xt. All right, output depends only on xt for t less than or equal to t naught. So, causal system is causal if depends xt, that is output y t naught only on xt for t less than, that is output depends only on past values of xt, does not depend on future values of xt. That is to explain it plainly, the output depends only on and not future values of that is the output depends. So, a causal system is one in which the current output at the current time instant depends only on the past values of the input, it does not depend on the future values of the input signal. Such a system is known as a causal. This property is known as causality, that is the input causes the output. This property is termed as causality. This is termed as the causality property and arises from the English word cause, which means the input causes or the input explains the output. For instance, again, and if a system is not causal, it means non-causal, obviously implies system is not non-causal, implies system is not causal, okay, which means that output depends also on future values of the output signal depends also on future values of output signal depends also on future values of the input signal. For instance, again let us go back to a simple system, y t equals minus infinity to t x of tau d tau. You can see this is a causal system. Okay, this is a continuous time causal system because it depends on y t depends on all x t, all tau x tau tau less than or equal to t. Okay, because this depends on x tau tau less than or equal to t. That is the important property here. However, on the other hand, if you have a system, let us take a discrete time system such that y n equals 1 over 2 n plus 1 summation n equal to minus n to plus n x of n minus n, correct, x of n minus n. Okay, you can clearly see, okay, y equal to x of n x of summation x of n n equal to minus n n equal to minus n to plus n. Okay, or let us put it this way, y n equals 1 over 2 plus summation k equal to minus n to plus n x of k plus or x of n plus k, or x of n minus k. You can see this goes from n minus n. So, this depends on, so if you look at y n, this depends on it depends on x of, well, n minus n, x of n minus n plus 1, so on until x of n plus n. So, it also depends on the future values of x, that is the whole point. It also depends also on the future values of x n. Depends also on future values of x n, hence this is non-causal. Since the output depends not only on the past values but also on the future values of x n, this is non-causal. Okay, it is an example of a non-causal system. All right, so we have causal systems. So we are looking at systems, different types of systems. We are looking at a classification of systems. We have causal and non-causal systems. In a causal system, the current output depends only on the current input and past values of the input. However, in a non-causal system, the current output depends both on the past values of the input as well as the future values of the input. So, that is a non-causal system. All right. So, we will stop here and continue this discussion in the subsequent lectures.